This is Briggs Stratton Energy Solutions training on charge, discharge, and state of charge for our Phi and Amplify batteries. So Simplify Power has been around since 2010, and we are based on safe cobalt-free chemistry. We have essentially no risk of unmitigated thermal runaway. And what that means is that essentially the chemistry that we use will prevent our batteries from going through a thermal runaway event in which one battery can catch other batteries on fire. We're essentially the safest chemistry, LFP chemistry, and we publish our safety results. We are UL tested and certified. We have UL 1642, 1973, and 9540 at our system level. We've also gone through a UL 9540 cell module and unit level fire test, and those tests we publish. They're fairly uneventful. Those tests involve forcing a battery to go into a thermal runaway condition. And essentially, as you can see, if you look at the results of our testing, our batteries put themselves out. We have UN Department of Transportation certification 3480 and 38.3 on our batteries, which allows us to transport and even airship some of our batteries. And Simplify has been around for a long time, and we're proven. We're a US-based manufacturer. We do all of our assembly and our shipping from Oxnard, California. We've deployed in over 45 countries, and now we have over 300 megawatt hours installed worldwide. So there's a rich history for Simplify Power in terms of our batteries. We've got batteries out there in the field now 13 years old, outlasting our warranties. We've been tested, and in our early days, participated with US Army and Marine Corps testing as they were looking to update their heavier lead acid batteries to lithium, and they were concerned about the safety of lithium. And through our testing, we were able to demonstrate the safety of LFP chemistry. So it's a different type of lithium chemistry than most of the common types used in mobile applications. And most home applications are going to LFP chemistry, and even auto applications are going to LFP chemistry just because of the increased safety there. We also have a business model that demonstrates social impact, and we've donated to a large number of nonprofits over the years, and that's a fun part of working for a company like this. One of our principles is to provide simple solutions. So we have solutions where we are trying to make integration and use of batteries as simple as possible, both for the installers to install as well as for homeowners to utilize. So by using our backup systems, it allows homeowners to have critical backup and really allows for some energy independence. We can maximize resilience and, as I said, energy independence and energy security. So if you're in a location where the power goes out fairly regularly, you can keep those lights on by using battery backup. We also can create savings on utility bills. So if you have a low-cost method of generating electricity, providing battery backup to that system allows you to generate energy during the day when the sun is out or when the wind is going, and use it when you need. So as I said, we've got over 300 megawatt hours installed worldwide. We have a large number of distributors selling our batteries around the world. We've got a global footprint that's been growing. What's driving this industry? Daniel presented this slide at his talk last week when he talked about installing our batteries in harsh environments. And I'm not going to go through all of it, but I do want to highlight one important fact. In the top right, you can see that only 15% of all solar owners have battery storage, but 61% say they want battery storage, right? And that's a large market, right? And as everything is electrifying, as cars are going electric, as we have more and more strain on our utilities, and the increased likelihood of power outages. Battery backup is a growing market and is a good thing for installers to become involved doing. We have a large number of different products. We have products from small battery sizes all the way up to very large containerized high voltage solutions. And we'll be focusing mostly on our most common smaller batteries, the Phi and the Amplify batteries.
And Nathan, actually, we had a great question. Can you go back one slide, please?
Sure.
Dustin is asking, do you have any high voltage batteries rather than just 48-volt batteries that they've used in the past? As many of the new solar and storage battery inverters for the residential market are now high voltage.
Yes, that's a great question. So we have a whole high voltage and projects team, and they can do custom applications, but we do stacks. And so what you see in the top right there are stack controllers, and these are our high voltage battery offerings that go up to 1200 volts. They come in 24 or 48 volt sizes with I think it's 3.4 kilowatt hours. Daniel's at 3.4 or 3.8 for the high voltage batteries. All right, well, we're not sure.
4.3. I'm sorry, I was muted there. 4.3.
4.3. Thank you, Daniel. And so they come in blocks of that size, and we can do all the way up to the megawatt scale if you have a larger application, or even if you just have a high voltage application, a single stack controller might serve you well. And we do have offerings that we are planning to come out with soon with some of those new larger systems that are coming out. So great question, thank you. Yes, we have a whole range of high voltage options. We also have battery cabinets. So if you're installing outdoors, we have NEMA 3R rated battery cabinets, and we even have a cabinet which we call the access cabinet, which can house an inverter, and so we can have a kind of plug and play option there. On the right side is our new ESS system. These are larger format batteries at 4.98 kilowatt hours, 48 volt options, but those are also outdoor rated batteries and outdoor rated inverters. Why would you choose Briggs & Stratton? Briggs & Stratton has a 115-year history, right? If you're buying and you care about that warranty, we have a 10-year flat warranty on all of our products. And so having that warranty there and having it backed by a company with a long history and a long tradition of innovation and success and manufacturing, you've got a solid company behind you for your warranty. Briggs & Stratton Energy Solutions has a whole array of different products for home backup and energy storage, as well as many other features. Right, the company has a large number of divisions, but we can provide with our ESS system, we can provide generators that will integrate into the inverter, as well as that inverter has charge controllers built into it. It can be AC coupled, it can be DC coupled. And so there are a lot of options moving forward with this ESS, which will be released shortly. So this is a training about our batteries and about charging and discharging the batteries. So I'm going to jump right in, talk a little bit about the chemistry. So a lithium-ion battery is a fairly generic term. There are lots of types of lithium-ion batteries, and they vary for the most part in what the cathode material is. What the material is, where the lithium atoms want to be. But there's also a negative terminal to the battery called the anode. And the difference in most of the the lithium chemistries is the cathode. So different types of batteries, you might hear the terms NMC, nickel, manganese, cobalt oxide, or a LCO battery which is a lithium cobalt oxide. Or an NCA battery is pretty common, especially in tools, power tools, lithium, nickel, cobalt, aluminum oxide. And you note one of the words there, I keep saying cobalt. So cobalt's a rare earth element. It's also a toxic element, and typically sourced with mining in Africa, where sometimes the mining practices can be somewhat questionable. And The other thing about cobalt is it makes the batteries, it gives the batteries a bit more energy. They have a slightly higher voltage to them, but it also makes that higher voltage makes them a little bit less safe. Our batteries do not use cobalt. We don't have that element in our batteries. We use iron instead. So our batteries are based on a lithium iron phosphate chemistry, which is the safest battery chemistry. And if you're installing battery backup at homes, it really should be the only chemistry that you consider, just because of the safety with in terms of fire safety, and in terms of not having that toxic element cobalt in there. It's also easier to recycle. There's another kind of battery that's labeled on the screen there, lithium titanate battery, and that actually has a different anode, but it typically uses a cobalt-based cathode. So that's not the only thing to consider about batteries. There's also something called the form factor, which is how the individual battery cells are made. There are 3 different principal types of cells: pouch cells, prismatic cells, and cylindrical cells. Pouch cells are the least durable. They're also the least costly to produce. They're very cheap, but you should never use these in a home backup situation. Battery storage with pouch cells is not very safe, and typically they're only used in very small applications. Prismatic cells are slightly larger cells. They typically can have a slightly higher energy density, and they're much better than pouch cells, but they are prone to swelling and contracting with temperature, and don't normally have as long of a life. They're slightly cheaper because they're manufactured in a plastic housing and they're in a large format. So on a kilowatt hour basis, they're a little bit cheaper. Cylindrical cells are the most expensive cells to manufacture, but they're also the longest lasting cells, and you're able to get a little bit more power out of them because they don't have quite as much of an issue with thermal migration, so the heat can get out a little bit faster. We use premium cylindrical cells in all of our batteries. We also are only using lithium iron phosphate. We're using the longest lasting and then the safest chemistry for our batteries. So I was asked why I harp on the chemistry difference. Here's an example of 2 pouch cells that have been punctured, and don't trust me, this is a online source, right? It's from an unbiased online video source. So Will Prowse has this do-it-yourself solar channel on YouTube where he tests batteries, and he drilled a hole in an NMC battery, and you can see what happens almost immediately if for some reason maybe a nail gun shoots into a battery, or there's a car accident. What can happen with an NMC battery is it can rapidly go into a thermal runaway event in which the electrolyte inside the battery is turning into a vapor and burning. He had to puncture an LFP battery something like 10 or 12 times in order to even get it to off gas, and you see the difference there on the screen. It's pretty evident. The NMC battery really rapidly releases its electrolyte and energy and has a much more rapid fire, whereas the LFP battery has a very slow discharge. Still is burning, but very slowly, and it's less of a dangerous concern. If you're interested in learning more about battery safety, I encourage you to visit Sandia National Labs, where they have a battery abuse and testing lab, where they show similar results with LFP and NMC. I'll link that there, and I'll be sending the slides to everyone, but this is not really a talk on battery chemistry and safety. We are going to move right into talking about charging and discharging of batteries. So I want to get into a couple of terms as we get started, just so we're all on the same page. People typically understand that batteries have an energy capacity. It's the amount of energy they can hold and deliver. This actually varies. It varies based on temperature, and it varies based on the discharge rate. So if I fill a water tank up with water, I know I'll get all of that water out when I open the valve and release it. When you charge a battery up and you discharge it, a little bit of that energy, it's typically around 2%, but it varies based on temperature, right? A little bit of that energy is converted to heat, and that's why things heat up, batteries heat up when they charge and discharge. And they heat up more when they're discharged quickly. So the energy capacity actually does vary a little bit, and it's typically specified at certain rates. Lithium batteries are a lot more efficient than lead acid batteries. And the discharge rate that is typically used is a C/5 discharge rate. So what does that mean? What is a C/5 discharge rate? It basically means that the charge within the battery is discharged over a 5-hour period. So if you're discharging one of our Amplify or our Phi batteries over a 5-hour period under standard temperature conditions, you're going to get about 3.8 kilowatt hours of energy out of that battery bank. The current capacity is the amount of charge the battery can hold and deliver. And that's typically specified in amp hours. And it used to be that batteries were labeled on size based on the number of amp hours, because almost all of the batteries were coming in 12-volt options. Now, with a variety of 24 and 48-volt options, specifying the current capacity is not really specifying the energy. And what people care about is how much energy the battery holds. What's the nominal voltage? This is a somewhat ambiguous term. The nominal voltage means the named voltage. The named voltage of a battery is typically based on 12-volt increments, right? So there's commonly the 12-volt batteries, 24-volt batteries, and 48. Although if you take a voltmeter and you measure the voltage on our batteries, it's normally a 48-volt battery would be above 48, and a 24-volt battery would be above 24 volts. It will reach those values, but the voltage of the battery changes depending on its state of charge. So the nominal voltage is the named voltage. It also is commonly referred to as the voltage of the battery at a 50% state of charge. So I'm going to use that definition of nominal voltage, the voltage of the battery at a 50% state of charge. For our 48-volt batteries, it's 51.2. And for our 24-volt batteries, it's 25.7, I believe, or 25.6. All right, so what is a C rate? So a C rate is the rate at which a battery is charged divided by the total number, the total current capacity of the battery. So typically it's easiest to understand a C rate in terms of how long it would take to discharge a 100% charged battery. But it measures the rate of battery charge divided by the total current capacity. So a C rate of 1 C would mean you would discharge a battery in 1 hour. A C rate of 2 C means twice that, twice as fast, right, would discharge a battery in 30 minutes. The maximum rating for our battery, and typically this is used to describe the maximum safe rate of continuous charge or discharge, for our batteries is C/2. For most of the prismatic cells, it's typically a little bit less. So as an example, a 20-hour battery can safely deliver 10 amps. As a 20 amp hour battery that can safely deliver 10 amps would be rated at C/2, right? So you can take the capacity of the battery in kilowatt hours, divide that by 2, and you'll get the power output of the battery. So a 3.8 kilowatt hour battery for us can discharge at 1/2 that, or 1.9 kilowatts continuously and safely. So the charging characteristics of our batteries are specified here. I'm just showing you our most common batteries. A 3.8 kilowatt hour Phi battery in 24 volts has 150 amp hour capacity. All of these batteries are rated at C/2. And then, so if it has 150 amp hour capacity, half of that, right, would be a C/2 charge rate. So we can charge that battery at 75 amps. Now, if you have a battery bank that has 3 batteries in parallel, and we always install our batteries only in parallel, never in series, right? If you have 3 batteries, then it would be 3 times 75 amps charging. So you could do up to 225 amps for a 3 battery bank for the 24 volt option. The 48 volt option has the same number of cells, but they're stacked, more of those cells are stacked in series to get that higher voltage. And so the amp hour capacity of the Phi 3.8 kilowatt hour battery is 75 amp hours. And so half of that would be a C/2 charging rate, and that's 37.5 amps per battery. It's the same value for the Amplify battery. So the Phi and Amplify battery maximum continuous safe charging rate is 37.5 amps per battery. So if you have a bank of 10 batteries, you could charge it at 375 amps. And then our largest battery, the outdoor rated wall hangable simplified 4.98 kilowatt hour battery, has a 97 amp hour capacity, and it can be charged at 48.5 amps per battery.
Nathan, we had a question, and I think you're going to get to this here in a second. It says, what is the, Thomas is asking, what is the rechargeability of an LFP battery at very low temperatures, such as 0 degrees Fahrenheit, which is significantly below freezing?
Yes, so that's a great question, Thomas, and I'm going to hold that for just a second because I am going to come to it today. I did throw a couple extra slides in here because that question came up last week, and I promised to address it this week.
And another question just popped up too, Nathan. What is the main difference between Phi and Amplify?
Good. So that's a great question. The big difference between the Phi battery, which is the second one in here on the screen, the 48-volt Phi battery, and the 48-volt Amplify battery, is closed loop communications. So the Amplify battery has a more sophisticated BMS, which is capable of communicating with other equipment, other batteries in your system. And so having that closed loop communications is important to people. And the closed loop communications is the big difference. Same battery pack inside, same premium cells in there, but a slightly more sophisticated BMS. And I'm going to talk about how that BMS can affect charging temperatures. Before I talk about how temperature impacts charging, let me just jump into the basics of charging. So when a battery is fully discharged, and I'm going to use a 48-volt option as an example here. So when a Phi 48-volt or an Amplify 48-volt battery is fully discharged, the voltage on that battery will be about 48.0 volts. In order to charge that battery, I have to apply a voltage larger than that, right? And so I have to have a voltage higher than the battery's voltage in order to drive charge the direction I want it to flow through the battery. So what I'm trying to do when I'm charging a battery is push the lithium ions into the anode or the graphite negative side of the cells. And so I have to apply a higher voltage. You're going to do this at a constant current. And so we normally set our batteries up under standard temperature conditions to charge at 37.5 amps. That's the C/2 rate for a 48-volt battery. So 37.5 amps per battery. So if I have 2 batteries, it would double to 75. So if I'm going to go at a constant current, that's what our charging cycle will look like. So I'm going to go at a constant current. Our charging cycle looks like what you can see here on the right. So I've got this graph. So the typical 2-cycle battery charging is a constant current cycle, and that's where the current stays flat for the first part of the cycle. That's a constant current cycle. It's termed the bulk cycle. The second part of a 2-cycle charging is the absorb cycle, and that's done at a constant voltage. So you see the CC and the CV here on the screen. If I want to push 37.5 amps of charge through a battery, I have to apply a certain voltage in order to do that. Right? And as the battery starts to charge, in order to keep supplying that 37.5 amps, I'm going to have to push harder and harder and harder to get that charge to move into the battery at a constant rate. And so you'll see what happens to the voltage is it gradually increases with time to supply that same current as the battery charges up. At the end of the bulk cycle, our batteries are going to be close to 90% charge, 90 to 95% state of charge. The next part of the charging cycle is to really top off the battery. It's called the absorb cycle, and that's done at a constant voltage. For our batteries, that voltage is 56 volts. And so when you set up a charge controller, it depending on the brand, it can have different names for these values that you're setting. Sometimes it can call it the bulk voltage because it's the voltage that the bulk cycle will end at. Sometimes they'll call it the absorbed voltage. Typically, it means the same thing. It's the voltage that you're going to reach and hold at for the absorb cycle to take place. Our absorb cycle is pretty short. The settings that we use for our batteries are just 0.1 hour or 6 minutes, holding at that constant 56 volts. Okay, so that's known as the absorb voltage. Some batteries will call it the bulk voltage or even the bulk termination voltage. There's another voltage not to be confused with this called the rebulk voltage, and that's the low voltage that your battery will reach when a charging cycle will restart. So as your battery is discharging, eventually that voltage will come down, and once it hits the rebulk voltage, maybe you set it at 51 volts or 52 volts or 50 volts, that's when the charging cycle will initiate. So when I'm referring to a bulk cycle or a bulk termination voltage, I'm talking about the 56 volts that we will go to for the absorb. And so that's constant voltage on absorb. And then there's a third part of the cycle, which is also a constant voltage, which is called float. Normally, we don't recommend using float. It really just keeps the batteries at 100% state of charge. We only recommend floating the batteries if you have a free energy source, like extra solar that's coming in that's not being used. And then if you want to keep your batteries 100% topped off, you can float the batteries at 54 volts.
Nathan, we had a question before we, Thomas is asking, will the battery limit the current level during the absorb cycle, or does the battery management system have to regulate it? Will the battery limit the current level during the absorb cycle?
So that's a great question, and I want to address it. So the BMS, I think there's a little bit of a confusion of terms there. So a battery management system, BMS, is typically referred to, it's referring to the computer inside the battery, which is monitoring this battery's state of charge and balancing the cells, etc. I think the question that was being asked is, can the battery control the current that's coming in? And the answer to that is no. BMS units have no way to control the rate of current coming into the battery. And I think the word that Thomas, that you were searching for was the charge controller or the charge control system. So that's a great question. In order to get the parameters set properly for charging a bank of batteries, it has to be done at the charge controller or the hybrid inverter. Whatever system is being used to charge the batteries, the charging parameters have to be set there. There's no way for the batteries to control, there's no dial inside the batteries where they can turn up the current or adjust the voltage themselves. That has to be done by the charging equipment. And for this reason, that's why I'm talking about these parameters that will need to be set in the charging equipment. And we have integration guides telling you how to make those settings in most of the common brands. And we're happy to help you do those settings if you're working with a system you don't know how to set up. So just a few notes here about the charging on our different batteries. We have small format batteries. We have a 12 volt and 24 volt 1.4 kilowatt hour batteries. These are popular for mobile applications like maybe an RV or a travel van. We even have a 0.73 kilowatt hour battery that comes in 12 and 24 volt options. Our more common batteries, here's the 3.8 kilowatt hour 5 battery. It is capable of a more rapid discharge, and I'll talk about that in a minute. This comes in 12 volts or 24 volts. It's 86 pounds. It's fairly heavy. It does come with wall bracket, or it can come with wall brackets if you order them. Those are a special order, but it can fit into these wall brackets that we sell. It also fits into our existing battery cabinets and works well with our ESS system. Here's the Amplify battery. Its charging parameters are listed here. It's got a nominal voltage of 51.2 volts DC. Again, nominal voltage there is the voltage of the battery at a 50% state of charge. It's a similar weight. I think it's slightly heavier than the Phi battery, and it has that closed loop communication there. It will fit the same wall brackets. One question we often get is, hey, I've already got the Phi batteries, but can I add Amplify batteries to my bank? And the answer is no. You don't want to mix batteries with the closed loop communications with batteries that don't have closed loop communications. Closed loop communications allows the batteries to talk to each other. And so if I have 3 Phi batteries and I had 3 Amplify batteries that I added, the Amplify batteries have no way of knowing those extra Phi batteries are there. So don't mix them. But if you're looking for closed loop communications, the Amplify battery has it. It also allows it to do charging. I'm going to come back to that question in lower temperatures. So I'll get to that in a second. And then our largest battery format is this 4.98 kilowatt hour battery. It charges at just under 50. It's 47.5 amps. This one is an outdoor rated battery, so you can mount this outdoors. It can be in the rain. It's a NEMA 3R rated battery. It's a bit heavier, so it weighs 180 pounds, but it hangs nicely on a wall bracket, so you can hang it up just about like hanging it on a picture. And I've installed these myself, and they're fairly easy to put. You mount a wall bracket up, and then you lift that battery onto the wall bracket. You can parallel up to 72 of these batteries. They also have that more advanced BMS system with closed loop communications. And so I can get into that more in the question and answers if you have questions about that particular battery. Here are our battery enclosures. So we have the smaller battery enclosure will hold 6 of our batteries, giving you 22.8 kilowatt hours of battery storage. That's an outdoor rated enclosure. We can make it with rain hoods if you're going to install it outdoors. It's got a built-in temperature controlled fan to keep the heat down inside the cabinets. And then in the larger cabinet, it can hold 12 batteries and hold up to 45.6 kilowatt hours of storage. The connections are all built in there, so it's a fairly easy wire. We call that our boss cabinet. And on the right side of the screen is the same cabinet. It's outfitted with a Solarc inverter. We have Schneider inverters that we have 9540 with as well. And then we're also going to be soon offering our own inverter in what's called an access cabinet. So when we have the inverter built in, it's more of a plug and play option. Pretty easy to install since everything is kind of pre-configured for you. And we can do this in an EMP hardened inverter as well. That is special order, but if you're interested in an EMP hardened inverter, we sell with the Solarcs with EMP hardening. So that's the access cabinet on the right. Let's talk a little bit about temperature. So first, I'm going to address the Phi batteries. So the small format Phi battery, as well as the larger format 48 or 24 volt Phi batteries. Their discharging temperature, they can be discharged safely down to -4 degrees Fahrenheit and all the way up to 140. So on the Celsius scale, that's -20 Celsius up to +60. On the charging side of things, the range is a little bit reduced. And so charging is reduced from 0 degrees Celsius up to 50 degrees Celsius. And the reason for that is that when lithium batteries, and this is not just our batteries, is any lithium ion battery with a graphite anode, when lithium batteries get cold, the lithium does not migrate very well, very quickly in between the graphite layers, a process called intercalation. And so getting between those layers is slowed down at low temperatures. And so typically manufacturers say their batteries cannot be charged below 0 Celsius. And that is true with our Phi battery. You want to make sure your charging equipment is monitoring temperature. and making sure not to charge this battery below 0 Celsius. On the Amplify battery and our larger 4.98 Simplify battery, these batteries actually can be discharged all the way down to -4 degrees Fahrenheit, but at a reduced rate. And so I'll come to this. The discharge rating is the same in all the batteries. They can be discharged safely at -4 Fahrenheit or -20 degrees Celsius, and discharged all the way up to 60 degrees Celsius. So let's talk a little bit more about that in a second. I'll come back to that. I'm not leaving that topic. But on the charging characteristics for a typical 5 battery, so I just showed you that battery has to be above 0 for charging to happen. We're going to charge it at a C/2 rate. And the maximum charge that that battery can take, this is the maximum safe charging rate, is 37.5 amps each. That means each battery. So if you have 2 batteries, it would double, 3 batteries, it would triple, etc. Typically, the charging equipment and not the battery is your limitation. But if you're using AC to charge, you want to be very careful. So with the 24-volt option, you can actually charge it a bit faster because it has a larger current capacity. It has a larger total charge capacity. And so you can charge that one at 75 amps for the 24-volt option. That's per battery again. And then the smaller format batteries, the charging rates are specified there. So do be careful if you have multiple charging sources running at the same time. So we'll sometimes get people that have 3 or 4 charge controllers all running at the same time. They've bought one and then they've upgraded their system and buy another out back or something like that. So just keep in mind that you have to pay attention to the maximum output of each of those. So if they're all going at the same time, you could damage the batteries if they're not properly programmed. So this came up as a question earlier. The BMS is there to balance the cells and protect the battery. There are fuses on these batteries, but you can still damage the batteries with improper charging rates. So be careful. Use the settings that are recommended. So you want to make sure to limit charge rate on your charge controller. And if you've got an inverter charging the batteries from AC, you want to make sure that you're limiting that charging rate to 37.5 amps per battery. If you have an Amplify battery with a proper equipment that has closed loop communications like a Solarc or our inverter, then the battery can communicate the rate at which it wants to be charged, and it will auto-populate those settings with the appropriate programming. AC coupled systems have further requirements in terms of setting the charging parameters, because typically for AC coupled systems, they're either charging at their full rate, right, or they're not charging at all. And so you want to make sure to always size your battery bank with enough batteries, right, that it can handle the full charging from your AC coupled system.
Yeah, Nathan, we had you just answered the question. Somebody asked, what brands can the Amplify battery communicate with? And you had mentioned our inverter and Solarc. The person's asking, what are the odds of it working correctly with other brands that we have not tested? I do know we don't support that. If you want to elaborate.
Yeah, sure. So we are in the process of getting the communications working with our Schneider inverters. We already have 9540 with Schneider. We had closed loop communications working with SMA, but they had a firmware upgrade that's caused some problems, and we're still our engineering team is working to resolve those. So right now, the answer to your question is the Solarc and the Briggs Stratton inverter. Very soon, I hope that will also include the Schneider XW and XW Pros. And we've been in discussion with Outback to get closed loop communications working with those as well as a discussion with Midnight Solar to get their charge controllers communicating with our Amplify batteries. But those are still in process. So the answer to the question right now is just the Solarc and the Briggs Stratton.
And it would be the Sunny Island?
Yes.
Thank you.
Let me go back, and we can talk more about inverters and closed loop communication at the end. Let me go back and tell you about how the Amplify battery can actually charge itself at -4°F, so at really cold temperatures, -20°C. So the Amplify battery has a closed loop communication system, right? And it can dictate to the charging equipment, the inverter, typically the hybrid inverter, how quickly it wants to be charged. And what the Amplify battery can do is it says, you know, if it's -20°C, and I'm going to do this in Celsius, if it's -20°C, the Amplify battery will say, start charging me at just 1 amp. Notice that that's very small compared to the 37.5 amps that it can normally charge at. But what happens when you start charging a battery is the temperature of the cells start to warm up. And the Amplify BMS is monitoring the temperature of the BMS and the temperature of the cells and the cell packs in a number of different locations. And as those cells warm, even though outside temperature might still stay at -20 or below, the battery cell temperature will start to increase. So it charges at 1 amp for a while until the cell temperature comes up even higher. And as that cell temperature reaches -10°C, it switches to 3 amps. As that temperature rises even more, it'll switch to 20 amps. And then eventually it'll be charging at 37.5 amps. And typically the cell temperature is above ambient temperature, because when a battery is cycled, there's what's called internal resistance, and there's always some heat generated inside the battery. So if you are in an ambient temperature that's very cold, and your battery is inside some type of enclosure, it's very likely that you can charge your battery. And so you can also discharge that battery down to -20°C as well. And so if there's some charging and discharging happening, typically about 2% of the energy of the battery, it's higher at low temperatures, but is converted to heat. And so it heats itself and is able to increase that charge rate. So hopefully I've answered that question. If, however, you get even colder than that, right, even colder than -20°C, so then the battery management system will go into a fault and it'll protect itself. So if the temperature is -40°C, I don't know if that happens. Maybe that's a little colder than we can normally get to, but I do remember in upstate New York hitting -30 Fahrenheit when I was a kid, so it can happen. The battery will open up the contactor and it will prevent charging and discharging until the temperature comes back to that -20°C range, and then the contactor will close and the battery will be able to operate again. Okay, so on charging characteristics of the 5 batteries, we need to make sure that we're using compatible charging equipment. Now, most modern equipment is designed for charging lithium batteries, but if you're using older equipment, make sure that the set points are able to be properly set for lithium batteries, and specifically for our lithium batteries. So if you don't have the ability to control the bulk and absorb voltage, do not use that charging equipment. Right? You need to be using equipment where you can program the appropriate settings in. Now, sometimes the absorb setting, you won't be able to set a time limit for that. What do we do for that, Daniel? When you can't set the absorb time to 6 minutes, what can you do?
We can adjust it to where the end amps, and if it's 2% of the battery bank's amp hour capacity would be the limit, and we would then stop that charge rate.
Great, thank you. Exactly, right? So if you can't set the time on your absorb cycle, what you can do is just set the end amps, and that's the rate. So what the charge controller will do is it will hold that voltage constant at 56 volts until the amperage drops to 2% of the battery bank's capacity. So if you had 150 amp battery bank capacity, 150 amp hour battery bank capacity, you would set it to 2% of that, which would be 3 amps. So once we're at 56 volts and the amperage keeps coming down and down and down, and once it hits 3 amps, it can cut it off there. So either use that 2% end amps rule, or the 56 volts for 6 minutes, a tenth of an hour. If you end up needing an external charger, maybe your battery bank is down and you don't have AC charging because you're not connected to, you don't have appropriate inverter connection, you can get an external plug-in charger. And we have a list of approved chargers on our website, and you can find that in the manual as well. Daniel, what's the one you recommend most frequently?
I love the IOTA. IOTA makes a great product. It should be noted that's a power supply, not a battery charger. We had another question, and I'm not sure if I'm getting this right, David, so correct us if we're not, is how is the current setting affected by aging batteries? And I think he may be referring to that 2% end amps. If you have an aging battery, is the capacity not less? Would that affect it?
Yeah, so with our batteries, again, we're using premium cells. We've got batteries that are going to last for, depending on how you program them, but if you program them to do a 20% to discharge it down to a depth of about 20% state of charge, you're looking at about 10,000 cycles, which would be 27 years if you cycle once daily. And so even after 10,000 cycles, 10 years of cycling, our batteries typically still have about 80 to 90% of the original capacity left in them. So there's not a huge difference in the amp hour capacity. So I think the answer to your question would be, yeah, it would be slightly affected. But we're talking about maybe a 10% change in that 3 amps, right? So 3 to 2.7 or something like that. So it's a good question, but for the lithium batteries, especially LFP batteries, there's not a huge variation as the batteries age. Much different from a lead acid battery, where the surface area of the battery is where the chemical reaction is happening, and that surface area can get covered and sulfonated, and you lose a lot of the bank with time fairly quickly, even with deep cycle lead acid batteries.
One final question. I know we got a lot of great questions. It's been a great topic. You just mentioned that if we cycle our battery down to a 20% state of charge, or 20% state of charge, or 80% depth of discharge, what if we raise that and we cycle the batteries even less deeply? Will that increase past 10,000 cycles?
It's a good question. And again, I think that the answer is unclear. If we saw a huge difference, I think we would probably advertise it. I think that 20% state of charge is not that low. And to my knowledge, we don't have numbers like 15,000 cycles if you only do a 50% depth of discharge. Because batteries are fairly expensive, right? Most people are wanting to get their value out of the battery by discharging and using that full capacity of the battery. I can tell you that there is a big difference between discharging to a 20% depth of discharge and discharging to a 10% depth of discharge. So if we discharge to only 10% of the battery's capacity remaining, we drop down from 10,000 cycles to closer to 5,000 cycles. That's still 13 years if cycled once a day, but that's a big difference. And if we discharge to 100% depth of discharge, take the batteries all the way down to 48 volts, then we're looking at only about 3,000 to 4,000 cycles. These are not exact numbers, right? It's not like when the battery hits, the 10,000 cycle, it self-destructs. It's more of a gradual. When we refer to the cycle life of a battery, that's the closest thing we have kind of approximating the age of a battery, since each battery is treated differently. What I can say is that batteries experience the most amount of degradation when discharged very fast, because that generates a lot of heat, which can result in electrolyte breakdown, Once, if you discharge very rapidly or take lots of power out of your batteries really quickly. The other thing to say is that, you know, it's still thousands of cycles, 3,000 plus cycles, taking the battery all the way down to 0%. So occasionally dropping that battery to a 0% state of charge is going to have very little impact on it. But doing that every day repeatedly for a long time can damage the cells. So it's kind of a gray area. I'd love to give you an exact number, and we, you know, the 10,000 is an approximation, but we've done a decent amount of testing on our batteries, and even after, you know, years, we're still seeing, even after, you know, 10 years, we're still guaranteeing 80% of the original capacity with our warranty, right? And our warranty allows you to do 100% depth of discharge as many times as you can over a 10-year period. We have a flat, pretty simple warranty because we really believe in our product. Okay, so I think I'm spending a little bit too much time on that, so let me keep moving on. Let's talk about discharging the batteries. So on the discharge side of things, we can actually surge the batteries, and so they're capable of discharging at higher amperages for shorter amounts of time. So if I have a battery under standard temperature conditions like room temperature, I can actually pull 80 amps out of the Phi batteries. So 80 amps out of both the 24 volt and the 48 volt. So a C/2 discharge. So if I'm going to do it continuously, I would want to use 75 amps per battery for the 24 volt and 37.5 amps for the 48 volt battery. But if I want to just pull a short amount of current out for a limited time, both of those batteries can surge to 80 amps. The limitation there is really the amount of current running through the BMS. On the Amplify battery with that larger BMS, that battery can surge to 100 amps for 10 minutes. And surging at 100 amps at you know, a voltage above 50 volts, that's 5,000 watts out of a single battery. Now that's limited, right? You can only do that for about 10 minutes. If you do that too long, it'll produce too much heat inside the battery, which can damage it if you do it for a long period. But there is that surge ability there. And so that's one big difference between the discharging and the charging cycles. All still rated at C/2 for continuous use. When I discharge a battery, you'll notice something that happens, and that's there's a drop in voltage. And so a simple circuit would show you that there's some internal resistance inside a battery. And so if a battery is sitting at 54 volts and I start to discharge it rapidly, the voltage will drop. And it's not because the state of charge is rapidly dropped or instantaneously dropped. It's because there's a voltage loss kind of inside the battery. And that occurs, that's proportional to the current you're drawing out of the battery. So what I'm showing you here is discharge cycles of a battery that starts at 100% state of charge over here on the left. You can see the voltage that it's starting at. And then as I start to discharge it, gradually that voltage drops, right? And this, a C/5 discharge rate, this whole graph would take 5 hours to generate. But you can notice that if I discharge at a rate of C/2, that would mean if I do it and discharge the battery in 2 hours, right? The voltage of that battery at the same state of charge at 90% charged, only 10% discharged, right, is about 0.6 volts below what it is at the C/5 discharge rate. Right, so the more rapidly you're discharging the battery, the lower the voltage will appear. As soon as you stop discharging the battery, you'll see the voltage jump up a little bit, right? And the reason for that is you're not having that ohmic loss of voltage. There's also a variation with temperature, and this is most pronounced when you're discharging your battery under very cold conditions. This is just for a single cell, and it's not even one of our cells, but this is an LFP cell, and I'm just showing you what happens at low temperatures. At low temperatures, the inside of the battery is much more viscous, and so for the lithium ions to migrate, they're going much more slowly, and so you'll have diminished capacity from the battery when you're discharging at low temperatures. The good thing is, is that as soon as the battery starts to discharge, its actual internal temperature starts to heat up. And so you don't stay on these curves, you typically will move up, right? This is forcing the cells to stay at a cold temperature. You'll see something that looks like this. So let's do an example here where we're looking at how quickly battery bank can be discharged. So what I have here is a 6 kilowatt Briggs Stratton inverter connected with 3 amplify batteries in a bank. And there are limitations on how quickly we can discharge the batteries. So for surge, the batteries are capable of outputting 80 amps for 10 minutes. But for continuous current, the batteries can only output 37.5 amps. So the power for continuous output is 37.5 amps times 51.2 volts. That's the nominal voltage. So about 1.9 kilowatts per battery. So you can already see if I'm using a 6 kilowatt battery and I'm getting less than 2 kilowatts each out of each of those batteries, right? The inverter is a little bit oversized for those batteries. And so ideally this system would have 4 of the 5 batteries instead of 3. Since it doesn't, since it only has 3 batteries capable of 5.86 kilowatts, what we could do is come into the inverter and program the maximum continuous discharge at 37.5 amps per battery times 3 batteries, or 112.5 amps. So this inverter is actually capable of 120 amps of discharge out of the battery bank, but we would want to limit it to protect the batteries to 112.5. You could also consider adding a 100 amp inline breaker. Now, why am I saying 100 amps even though you have 112 amp discharge? Well, breakers typically don't trip exactly at their full load, right? It takes longer for that to happen.
Nathan, we had one question. If you could go back one slide. The picture on the left there, we see some wires coming from the batteries going into that Midnight Solar combiner box.
Yes.
Do those wires need to be the same length, or can the battery management system remedy that?
Yeah, that's a great question. So yeah, the batteries running from, the cables running from a battery to the combiner box need to be the same length. And the reason for that is that when a large amount of current is being drawn through cables, there's a voltage drop, right? And so if the load is dropping dropping a voltage at the combiner below the battery voltage so that the battery starts discharging into the combiner, if one battery has a longer cable than the others, it will be outputting, there's more resistance in those longer wires, those longer cables, and so it will be outputting less current and do less of the work. And so that we equally load each of those 3 batteries, we want to have those cables all being equal length.
When they're in parallel. Go back one more slide. Thank you. That's great questions. What would the C, I think I'm not understanding this. What does the graph look like for C over 20? This graph here.
That's a great question. So let me see if I can go here. Let me come back to that question and I'll address C over 20. So C over 20, you're going to see very little voltage drop across the internal resistance of the battery because the current rate is so small. So it'll almost look like a resting voltage. So I'm going to come to that in a second. For the temperature graph, it's the same answer there. Since you're discharging so slowly, you see less of a temperature effect. This is a C over 2 discharge cycle of a LFP battery cell. So I'll come back to that question. It was a good question. So again, I've given you the values for each of the batteries in terms of what they're capable of surging at, or what they're capable of doing continuously. And you want to make that calculation for your battery bank. If you ever need help doing those calculations or sizing your battery bank, we have a whole army of engineers ready to help you design your system. And so feel free to give us a call. Consider using inline breakers for protection. And be careful where you locate those breakers. Battery breakers, there needs to be a disconnect between your battery bank and your inverter, but all of our batteries have breakers built into them. They have 100 amp breakers built in, so that can act as a disconnect. So you're not required to install anything additional, but a number of installers like to install a separate disconnect for the battery bank in case they're, servicing an inverter, et cetera, or just want to be able to disconnect that battery bank. Maybe they're leaving for some time, don't want that inverter to draw down the battery bank. And so adding a separate disconnect there allows you to cut the battery bank off from the inverter to avoid that piracy draw if there's no energy coming in. Also, always consider the AC output of the inverter. If you are using the inverter as an AC charging source, make sure that you're not charging too rapidly. And be careful on sizing your breaker. So here's a couple of examples what I was talking about on a breaker. This is a 60 amp breaker, but notice that if I load this 60 amp breaker at 100% of its rated capacity, if I put 60 amps in this breaker, even after 500 seconds, it's still not going to trip, right? So this breaker needs to hit an amperage above that 60 amp and in order to trip. So all breakers are a little bit different, right? So this is a trip curve on a different 60 amp breaker, and notice that it will trip after just maybe a few seconds. This is a log scale on the bottom. So it looks like maybe about 3 seconds it'll trip at 60 amps. So there is a certain amount of time for a breaker to be able to trip. So pay attention to those trip curves when you are picking out a breaker. Here's another 60 amp breaker, and notice it doesn't even trip until we're at about 140% of that 60 amps. So somewhere around 90 amps over a 500 second range. And I'm sorry, this is a fuse, not a breaker. So just keep those in mind when you're designing protection for your system. Let's talk a little bit about the voltage of the battery. And what I'm referring to is the state of charge and resting state of charge and its relationship to voltage. So what do I mean by resting? I mean that the battery is not in a state, it's not in a charging cycle, and it's not in a discharging cycle. There's no amperage coming into or going out of the battery or the battery bank. There's no load connected. It's not powering a load, right? And so we'll look at the voltage versus the state of charge. And it really depends, if your battery is really resting, it's easy to determine the state of charge of the battery based off the voltage. But if the battery is not resting, then it's a somewhat complicated calculation that the inverter needs to do. And for that reason, the state of charge monitors can often be off a bit. So you can find examples for programming and battery monitoring in our integration guides. And the Amplify battery and the Simplify battery with their advanced BMS units and their closed-loop communications can provide a lot of information and very accurate high-level state of charge readings that can be at the battery level, meaning you can get them from all individual batteries with monitoring. So here's an example of a 48-volt battery. When it's 100% state of charge, we're looking at actually above 53 volts, so 53.2 volts. This depends a little bit on temperature, and these measurements are at room temperature 25 Celsius. As the battery is discharged, now this is not a discharge curve, so as the battery is discharged, I stop, let the battery rest, and then monitor its voltage again. Once I get down to 50%, you can see that I will be at 52.4 volts. When I go farther down, right, I get to about 52.2, it looks like on this curve. This is for, again, for a resting battery, I'm at 30% state of charge. Once I get down to about 10%, I'm below 51 volts. I'm heading towards 50. Notice it starts to drop off rather quickly. And so at 0% state of charge, I'm all the way down at 48 volts. So if you're at 48 volts for a resting battery, then you're at a 0% state of charge. Okay. And so there's a low battery cutout points that you can set into your inverter to have it turn off once your battery hits this low value. And if you want to make your battery last longer, right, you use a higher low battery cutout value. We typically recommend using a 20% state of charge. So here are the levels at C/2 rating. So at a C/2 rating, we're looking at 50 volts as 20% state of charge. 100% state of charge. Notice this value is less than that 53.4 that I just showed you, right? Because when the battery is discharging at a rate of C/2, there's a voltage drop inside the battery due to the internal resistance. Okay, let's jump. I'm going to go break past this. Let's jump over to our Elite Installer program. I want to highlight this program for you. We've been growing it fairly rapidly. We've got just something like 30 or 40 people signed up just this past month. And I want to highlight some of the advantages. If you are an installer company, one of the things we do is we put you on an our installer map, our where to buy map, and our customers are often looking for local experts in installing our systems. By joining the program, we'll send you a free swag pack. You also get some extra incentives. There's a $25 cash back if you sign up as an Elite installer with our company. We pay this out quarterly and base it off of your warranty registrations. So if you register 20 batteries in that quarter, we'll send you $25 times those 20 batteries. And so you're also eligible for some special promotions. We're currently running some promotions on batteries where you can actually earn $100 back per battery installed as an Elite installer. So look into that. And we also have our sales team recommending our customers when they call in, they ask us, hey, who can you recommend in our area? We go to our Elite installer map and pick companies off there. So I encourage you to consider signing up for our Elite Installer program. If you've learned something today and you want to learn a little bit more, I'll be sending a copy of this slide deck out to you. And so you're welcome to utilize the links that are here. We have online learn at your own pace classes on the Briggs Stratton Power Academy. The webinars, you've obviously made it to this one. Our training calendar appears on our website. Recorded training, so if you miss a training and you would like to go back and review the topics or see what you missed, go to our YouTube channel, just search Simplify Power on YouTube and it'll bring up our channel, and we put all of our old trainings on there. You can't get NABCEP credits from YouTube, but you can see all of our old trainings there. And of course, all of our product documentation, installation manuals are on our website. So please do look into those and the integration guides when you're installing a system. So if you click on support on our website, you'll find all of those here, as well as how-to videos, and a link to our training calendar is here. It's also at the very top. Our where to buy map is there. And so if you become one of our Elite installers, we'll get you set up and shown on that map. So thank you for your attendance today. If you're here for NABCEP credits, please send an email to Daniel and I, training@simplifypower.com. Let us know how you want your name spelled on your NABCEP certificate, and we will get that sent out to you. If you have any other questions, feel free to pop them into the Q&A, or feel free to contact us. Our phone number is there. Our email is there. Let us know how we can help. We can put you in touch with an engineer if you need some help designing your system. So thank you. Daniel, are there any other questions that you haven't been able to answer?
One last question. Somebody's asking, so anything below 48 volts on a 48 volt battery, does it damage the battery? And I'm going to ask a question, what happens when you do discharge it below 48 volts? Is it?
Yeah, it's a good question, Daniel. Can the battery, I mean, is 48 volts really 0% state of charge? No, it might be around 1% state of charge, right? You can go even lower than that. When you go much lower than that, you're getting a significant amount of charge polarization. And the answer is, I'm not exactly sure. One thing I can tell you is that you're significantly depleting all of the lithium out of the anode layer. The other thing to tell you is that the battery BMS system might open up the contactor to prevent further discharge, and you might need to plug in a wall charger. If you go below 46 volts, I think the contactor will open up to protect the battery. So on a physical level, Daniel, I can't tell you exactly why, if you discharge a battery too low, you can't get it to charge again, but you can kill the cells if you go much below 48 volts. And so the BMS does open up at 46 to protect the batteries. But yeah, it's a good question that I don't have a solid answer to, and I can dig deeper. If you want me to talk to the engineers, send me an email and we'll go more deeply into that.
Great. One last question.
Sure.
There's a gentleman, Andre, he had a bank of 5 48-volt batteries in October, fully charged to 56.4 volts. After a Canadian winter, where temperatures dropped down to -25 degrees centigrade, he returned in April after leaving in October. The voltage had dropped to 53.2. Is that normal? Is that a self-discharge, or why would we see something like that?
So the batteries themselves, if they're in a resting state of charge, shouldn't be at 56 volts. The charge controller itself will be at 56 volts when it's in a charging cycle. But as soon as the charging cycle ends, the voltage of the battery should drop down to about 53.5 volts. So a fully charged battery, when the charge controller is not running, will be at about 53.5 volts. It depends a little bit, as I said, on the temperature. And then the batteries have a very low self-consumption rate, something like, Daniel, I think the number is 1% a month or so,
Yes.
right? It's slightly higher for the Amplify batteries if they're left switched on, because the BMS does use some charge, right? It does use some energy. But if the batteries were switched off, there should be a very low self-discharge, around 1% a month. And so those batteries at 53.2 are still above 90% state of charge. So yes, that does sound like normal numbers to me.
Thank you, Nathan. That's all we had for today.
And that's a great question. And it's important to keep in mind when you're looking at a voltage, if you're in a charge cycle, you're not looking at the battery's voltage. You're looking at the charge controller's voltage, which has to be above the battery voltage in order to charge the batteries.
Yeah, and Andre responded here, the batteries were switched off.
Okay, good. Yeah, so you know, with the batteries switched off, we're looking at a very slow discharge rate, and coming back after months and finding them at 53.2 means you're still coming back and finding them above 90% state of charge. It's a good question. Thank you. Any other questions, Daniel?
We had a comment. David is mentioning, he says, very low discharge stresses the chemistry and reduces the life of the battery. Low discharged batteries may require special algorithms to incrementally recharge them. Have you heard something like that?
Certainly. I know it stresses the chemistry, and I appreciate somebody chiming in with that. What I don't know is specifically how it stresses the chemistry. It might actually stress the cathode and anode lattice, like the cathode is the metal. It's not really a lattice. It's a spray cast nano structured LFP kind of solid with electrolyte mixed in with it. And then the anode is typically layers of graphite. It's graphite in layers. So I'm not exactly sure what the stress on the chemistry is. And I'll ask our lead engineer on that, because that's a good question, and I should know more about that. But I think that it might actually stress the solid structures themselves by being very low, and it certainly would heavily deplete lithium out of the graphite. But I'm kind of just thinking out loud on air now. So
thank you, Nathan. That's all the questions we had for today.
They were great. Thank you. And feel free to email us if you want to continue the conversation. We love the questions. Thanks so much for your attendance, everyone.
Thank you, Nathan.